Hi everyone. So part 2 of the learning material. Today again we are going to continue with casting processes. We are going to discuss about casting technology, heating and pouring process, and solidification and cooling. Here, heating of the material. We are going to start with heating the material. How much heat need to be supplied for a metal to convert it into molten metal till pouring temperature. This is very important in casting. So casting, one of the place where we supply energy or heat energy, you can understand it in 3 stages. The first stage, we supply heat to raise the temperature to the melting point. Then the heat of fusion, the heat required to convert solid metal to liquid metal, that is called heat of fusion. Again, you are supplying heat. The heat required to raise the molten metal to the desired temperature till the pouring temperature. The heating process takes place in 3 stages, as I explained here. Heat to raise the temperature to the melting point, the heat required to change solid metal to liquid metal, that is called heat of fusion, then heat to raise the molten metal to the desired temperature. This can be written in equation. How it can be written is the heat required is equal to, heat supplied is equal to rho V, density times volume. What is density times volume? It is mass. So mass multiplied by specific heat of the solid times Tm minus T naught. So look at this equation. Whenever we talk about heat transfer, we give an equation mc delta T. What is m? M is rho times V, density times volume. What is C? C is specific heat of the solid material. What is delta T? Temperature difference. What is temperature difference? So as I explained before, first stage you need to heat to raise the temperature to the melting point. That means solid metal from room temperature till melting point, that is Tm minus T naught. So M means rho V, Mc specific heat of the solid material times delta T, temperature of melting point minus minus the ambient or room temperature. This will give you the total heat supply to raise the temperature till melting point. Plus, now what do you need? You need heat of fusion. So heat of fusion to convert solid to liquid, second stage, and the third stage is to convert or to raise the temperature of the molten metal to the pouring temperature. So again, MC, this is common for all these 3 factors. You can see here mass times MC. So now specific heat of the liquid, now the metal is in molten stage, liquid stage, hence specific heat of the liquid times Tp minus Tm. Tp is the pouring temperature and Tm is the melting temperature. So M is common, rho V is M, which is common, then uh, then the heat required to rise till melting point. This is for the solid. Then heat of fusion to change solid to liquid. Then the heat required to increase the temperature of liquid to the pouring temperature. This is how we calculate the total required to raise the temperature of metal to the pouring temperature. Now, the analysis of pouring, when we analyze the pouring, we have the equation, we have to apply Bernoulli's equation, we have to apply the flow of a liquid, fluid concepts, fluid mechanics we have to apply here to understand the pouring process. So in a pouring process, we have, let us take 2 sections. One section is the pouring point. At that point, we can say the section 1, we have H1, which is the head energy, head pressure, kinetic energy and friction. So three energies are there in during the flow. Head due to height, pressure energy, kinetic energy, and friction energy. So H1, the height, plus P1 over rho, pressure head, plus V1 square over 2G, kinetic energy, plus friction at at level 1 equal to H2 plus P2 over rho plus V2 square over 2G plus F2. So if you look at it, in a pouring, in a downspew normally the top level is considered as level 1 and bottom level is considered as level 2. So what happens is we are applying Bernoulli's equation between level 1 and level 2 at the start of pouring till it reaches the bottom side of the sprue. So take the sprue. I already explained sprue, runner, riser, etc. So take the sprue, and the top portion of the sprue is taken as 1 and bottom portion of the sprue is taken as 2. Apply Bernoulli's equation between 1 and 2. When we apply Bernoulli's equation between 1 and 2, we get height, we call it as head at 1 plus pressure energy plus kinetic energy plus friction is equal to head at 2, that means bottom side, plus pressure head plus kinetic head at bottom side plus friction F2. So when we analyze it carefully, we can see that the pressure head P1 over rho and P2 over rho are same. There is no change in pressure head, so we can cancel P1 over rho and P2 over rho. Friction F1 and F2 are same because we consider it as a smooth flow. Hence, they are same. F1 and F2 are same. So equation can be rewritten as H1 plus V1 or V1 square over 2G is equal to H2 plus V2 square over 2G. And using this equation, we can find the velocity at the bottom side of the sprue. So you can see here H1 plus V1 square over 2G is equal to H2 plus V2 square over 2G. This is after reduction of the equation. And if you take the top side of the sprue, top side at point 1, top level, velocity is 0. So hence at point 1, V1 square over 2G becomes 0, and then H1 is equal to H2 plus V2 square over 2G. So here we can write H1 is equal to V2 square over 2G. What happened to H2 is H2 is considered as the bottom level. If point 2 is considered as the reference plane, the base plane. So hence H2, the height from the reference is 0. The H2, it's level 2 itself is taken as the baseline or reference line. Hence H2, the height becomes 0. So H1 can be written as V2 square over 2G. So the velocity at which molten metal reaches the downside or the bottom side of the sprue, V, is equal to square root of 2GH. G is the acceleration due to T, and h is the height of the sprue. Now we can apply continuity equation also in here. When we apply continuity equation says constant flow throughout the area. So if you can see here, A1 V1, area times velocity, is equal to area 2 times velocity. So as area decreases, velocity increases. So the total flow remains the same, Q remains the same. So A1 V1 is equal to A2 V2. A1 is the area at 1 and V1 is the velocity at 1. A2 is the area at 2 and V2 is the velocity at 2. So as area decreases, what happens? Velocity increases. So in order to increase the velocity, the sprue is the shape of the sprue is like tapered, so that area decreases and velocity increases. So this is the shape what is given for a sprue in a casting process. So this will help the molten metal to reach the cavity quickly because the velocity increases. So enough velocity will be produced for the molten metal whenever it reaches the bottom side of the screw, because we have given a tapering in the screw, and hence area decreases and speed velocity increases. Now the time required for the molten metal to fill the mold is V over Q. V is the volume of the mold cavity and Q is the volume flow rate. So this is how we calculate the time required for filling the mold cavity. The volume of the mold cavity divided by Q, the volume flow rate. Now let us take an example here. We have a sprue 20 centimeter long, area 2.5 centimeter square. The sprue feeds horizontal runner leading into a mold cavity whose volume is 1560 centimeter cube. So here mold cavity, the volume is given, the base area is given 2.5 centimeter square, height is given. We need to find velocity of molten metal at the base. So we have an equation, velocity equal to square root of 2gh, 2g times h, height 20 centimeter, we get velocity. Then we need to calculate volume rate of flow. Q is equal to area times velocity. Area is given as 2.5. 2.5 times velocity will give you the flow rate in centimeter square per second. Then time required for filling the cavity is equal to, you can see here, the volume divided by Q, V by Q. Volume is 1560 and Q is given in here. So we calculated Q as 495. So this will give you the time required for filling, which is 3.2 seconds. Now we have example 2 here. In here we have a shape. So we need to design a cylindrical riser with diameter to length ratio 1. This is a sand casting. The casting geometry is given in the figure. If the mold constant Cm is 19.5, determine the diameter, the specifications of the diameter, design a riser for this application, find the dimensions for this application, and remember the riser solidification time is 0.5 minutes longer than casting. So the solidification time for riser is 0.5 plus the solidification time for the casting. So this is the part to be produced. This area is hollow. You can see here rectangular hollow portion, and this area you can see a cylindrical area, and we have to calculate how much is the dimensions of the cylindrical. So first of all, which equation we have to use is known to you. The time required for the total solidification time, time required for solidification is equal to Cm, mold constant, times V over area raised to n. Cm and n are already given, they are constant. So V divided by A, volume divided by surface area to be calculated. So casting volume is volume times the volume. How to calculate? First, volume of the rectangular plate plus volume of the half disc plus volume of the upright tube minus volume of the rectangular cutout. How do we calculate it? I will explain. So let us take from here. So here we have this is consider a rectangular plate until here. So here the volume of the rectangular plate, which is given here, that is the first one. Then volume of the half disc. Volume of the half disc is this volume of the half disc. Then what we have is volume of the upright tube. This is the volume of the upright tube. Then we have to minus volume of the cutout portion. This is the cutout portion, we have to minus it. So we get volume, and then we can calculate the after calculating the volume, we can calculate the surface area. Surface area also, total area also can be calculated. We get total volume as 61.974 and total surface area is 203. Then after calculating volume and area, we need to calculate volume divided by area. So we got it. Then we can find for the casting total time required Cm, mold constant, times V over area, which is 0.305 raised to n. We get the casting time, then casting solidification time. Then riser, the condition is given here as 0.5 minutes longer. So casting time required for solidification in casting plus 0.5 will give you the time required for solidification for a riser. So riser volume is pi over 4 d square L because cylindrical section. L and D are same, so instead of L substitute D, we get pi over 4 d cube. Then area is circumferential area pi dl plus 2 times pi over 4 d square. We get 1.5 pi d square. Then V over area, we get it as d by 6. Just substitute in here, and then we get d from here, which is 2.065 inches, and L is the same as D. This is how we calculate the dimensions of a cylindrical riser. So we have designed a cylindrical riser for this particular casting. So for this casting, we need a cylindrical riser of diameter 2.065 inch and length 2.6065 inch. Thank you very much.